Suppose we have a circuit like this to solve. There are two possible ways of solving it. We can use the mesh analysis and write three equations and three unknowns. So we can always do it this way, but today we're going to use the Thévenin theorem. Okay, so we have to find the Thévenin equivalent voltage generator referred to terminals AB for these circuits and determine the current I flowing in branch AB. So let's read something about the Thévenin's theorem. The current in any load impedance connected to two terminals of a linear network is the same as if the load impedance were connected to a single generator whose EMF is equal to the open circuit voltage across the terminals and whose internal impedance is the impedance of the network looking back into these terminals with all the generators reduced to zero and replaced by their internal impedance. So let's start. It means that we can replace this circuit, the whole circuit here, all these generators, by a single generator whose voltage is the source is the open circuit voltage. It means it's the voltage between AB without this load. So it means VTH is VAB minus VBC at open load. And the internal impedance of this source is the impedance seen at the terminals looking in at terminals AB without these sources or these sources short circuited. Okay, so this is the impedance looking at these terminals with the voltages replaced by their internal impedances. And here we have our load ZL. So we can calculate the current using this formula. That's it. Let's calculate VTH EZTH. VTH is the open circuit voltage. We go back to our original. Here we have V1, V2. This is 30 and argument 0 degrees. This is 60 and 0 degrees. Okay. So the voltage, we can say that if we call this I1 and this I2, we can calculate VAB is equal to minus 3 times I1, and VBC is equal to 4 plus J6 times I2. I1 is V1 over Z1 is equal to 60 degrees. I will change this one over Z1. Z1 is 4 plus 5 minus 3, it means plus J2, and in polar form this is 60 degrees over 4. 4 is 4.472, argument 26.565, and this I1 is 13.416, and minus this, minus 26.565, and we can calculate now the VAB, VAC, and VBC. So it means VAB is VAC minus VBC. VAC is equal to minus 3 times this current, 13.416 minus 26.565, and this is 40.248 minus that's right, because there is minus 90 here as well, so minus 116.565 volt. So we write VAC is equal 40.248 minus 116.565. Okay, let's calculate now. I2 is equal to V2 over Z2, which is 9 plus J6. It's 30, 0 degrees, and here it's 10.82, 33.69 degrees, and we have 2.77 minus 33.69, and VBC is equal to 4 plus J6 times 2.77, argument minus 33.69, and it's 4, this is polar form, 2156.31 times 277 minus 33.69, and this is 20. This argument, this minus this, will give 22.62, and in algebraic form, 46 plus J 7 times 692, and we write it here. VBC is equal to 20, 18.46 plus J 7.692, and we can calculate now. Remember that this one in VAC in algebraic form is minus 18 minus J36. Now we can calculate VTH. VTH is equal VAB is equal to VAC minus VBC is equal to VAC minus 18 minus J36 minus 18.46 minus J7.692 This is minus 36.462 minus 43.692, and in polar form it's 56.91 minus 129.845. This is our VTH, so we can write VTH, we can write it here now, we needed only this. VTH is 56.91 minus 129.845. Now we can calculate ZTH. ZTH is, we replace this by short circuit, this one by short circuit, and we calculate the impedance seen from this. ZTH is equal, if we call this one as Z1 and this one Z2, they are in series, so we can say that ZTH is equal to Z1 is equal to this in parallel, it means 4 plus J5 times minus J3 over 4 plus J2. I'll have it here. That's right, it's 15 minus J12 over 4 plus J2, and this one in polar form 19.21, argument minus 38.66. Here the denominator is 4.472, 26.565, and the result is let's calculate it. Z1 is 4.2956, argument minus 65.225, in algebraic form 1.8 minus J3.9. Let's write it here. Z1 is 1.8 minus J3.9. Is it right? That's right. Now let's calculate Z2. Z2 here. Z2 is this in parallel with this is 5 times 4 plus J6 over 9 plus J6, which is equal to 20 plus J30 over 9 plus J6. In polar form it's 36.055, and argument 56.31 over 10.816, argument 33.69. the result is 3.333, argument 22.62, which will give us in algebraic form 3.077 plus J 1.282. So plus 3.077 plus J 1.282, and the result is 4.877 minus J 2.618 in polar form is 5.535 minus 28.227. This is ZTH. So we have now we can add, we can calculate I is VTH over ZTH plus ZL. VTH is 56.91 minus 129.845 over ZTH is equal to 4.877 minus J.268 plus the impedance of the load impedance is don't remember, is 10 minus J8, 10 minus J8, and this will give us 56.91 minus 129.845 over 14.877 minus J 10.618, and this is in polar form 56.91 minus 129.845 over the sum of the two in polar form, it's 18.277 argument minus 35.516, and the result is 3.14 argument this plus this. It means minus 94.33, of course, amps, and in algebraic form is minus 0.235 minus J 3.105 amps, and that's it. So we have calculated the current using the Thévenin's theorem, and I hope that I made no numerical mistakes, but the method is correct. Thanks very much.